This is Aaron Brown,
And my name's Andy Brown.
not
related.
no relation there, but we've got the two Browns here, and we're doing the localization walkthrough project today, also known as the Kidnap vehicle. So,
Yeah, should we talk a bit about who we are? My name's Andy, but I work here helping make these courses. Currently working on a path planning course, which will be coming out shortly, and I formerly was working on this course.
yeah, and I'm a content developer. I'm also working on the path planning project right now, and a lot of fun work going on with the simulator for that. So it should be really cool when term 3 starts up and you can get your hands on that. So for today's project, essentially what we have is this car, and it's got these lousy GPS measurements that it's using. So for its X, Y, and theta. And essentially we want to localize really well where this vehicle's at. So we're going to be using LiDAR in this instance to actually take measurements of landmarks that are around. And based on a map that we're given, we see how close these measurements lie to the map. And if they're really close, then we give that particle really high weight. So we have many particles with a particle filter, and they all start off with very random values. As it goes around and it does its update, it looks at the weights that have the highest, and those survive on. And in the end, we look at the particle with the highest weight, and that's our representative of where the vehicle actually is in its environment.
And it always amazes me. Maybe we should show the animation that we have. Maybe this would be a good time to switch to screen sharing. Show the project actually in the simulator. It's amazing to me that particle filters actually work as well as they do. They turn out to be very useful for low-dimensional state spaces. Just create a bunch of particles, compare their view of the world, or imagine what their view of the world would be compared to what you see, and that turns out to work. And then resample. But we don't have to go too much into the theory because you guys got a lot of that in the class. You probably want to know more about how to actually do this.
Yeah, and run the project. So this is the latest update of the project. So it is using the new Term 2 simulator. And right now, I guess we'll go ahead and switch over to screen share mode and check it out.
If you guys have any questions as we're going along, you can keep going. But if you guys have any questions as we're going along, feel free to put them into the chat to the right of the video box.
So this is my repository for the Car ND Kidnap vehicle. When you're first starting off, you just kind of go over to GitHub over here. You'd fork it and then go ahead and clone that off, and that's the repository that you would be working with. Right now, I'm just going to go into Build, and I'm going to launch my particle filter. So we'll kind of see what it looks like if you have it all up and running. And then I'm going to go ahead and I downloaded the Term 2 sim. I'm running the Term 2 sim on Windows, and I'm running my code through Ubuntu Bash, and that's the latest 16.04. But you can also use 14.04, and that works well too. Booting up this simulator, and I'm going to go to the Kidnap vehicle project here. And it says I'm connected. So I'm going to go ahead and hit start. And what I'm seeing here is this blue circle is the best particle that I have. It's the particle with the highest weight. And you'll notice that it's basically right on top of my car. I can go ahead and zoom in on here. Also, I have some additional graphic features happening right now. I see these kind of like blue and green lasers. Basically, the blue lasers belong to the best particle, and the green belong to the car itself. And they're right on top of each other, so that's good. So that means my transformations are working well for that.
Speaking of which, transformations, I don't know. Should we maybe talk a bit about how to think about doing this?
Yeah. So in earlier projects like the common filter, like the extended and unsensed common filters, we were kind of dealing with a stationary sensor, and we didn't have to worry about doing transformations really. But here, when we're doing our LiDAR measurements, it's all in respect to the vehicle, which is moving around with this LiDAR. And that means if we want to go from the vehicle's coordinate systems to the map coordinate systems, we're going to have to do some trig in order to do that.
Do you want to, maybe we could do this on the board, on the whiteboard.
Yeah, sure.
That's a good idea. So where is global coordinate system? Can you see that? It's not going to be the best, but we'll try to make it work. So this is x. This is our y-axis. What we wind up doing, so we also have our car. It's sitting somewhere in here. Maybe it's an angle. And it's got its own coordinate system. So its coordinate system, so if the car is facing this way, like up and to the right, this would be its x-axis. And this, on the left, would be its y-axis. But those aren't the only coordinate systems we're dealing with. Also, we have these thousands of particles potentially, depending on how many particles you set number of particles equal to. And each of those, we imagine, has its own little coordinate system. So if this one's facing this way, maybe, then it's got its own little x and its own y. And it can be tricky to reason about this many coordinate systems. There's definitely some trig involved in going from, thinking of how much does a little bit of x progress in the car's coordinate system translate into x progress in this coordinate system. It's, it requires a little bit of thought. I don't think it's worth writing those equations on the board right here. Because I don't think you'll be able to read them. But this is sort of what you're doing. And then at the end of the day, the reason you're doing this is because you want to compare the particle's view of the world, which you're thinking about in the point of view of the particle, to your own view of the world. And you can either do that. Actually, Aaron and I both solved have made our own solutions to this project. And in his solution, he transformed everything into the global coordinate system. And in mine, I transformed everything into the car's coordinate systems, and they both worked. But if you don't get that right, you can get some really, really weird behavior. And
there's some great debugging tools on the simulator too, where you can actually see which association you're making with the landmark. So is it the one you think it is? And it should be the one that's closest. If you actually have some sort of landmark, let's say right here, and this is the particle right here, and it maps out and it's saying, okay, well, I think the measurement's right here. If you take the closest landmark to that measurement, that's what you're going to be using for association. I also kind of want to show something.
What do you mean when you say data association? I just want to make sure, because
yeah, so if you have multiple landmarks that you're seeing at any given time, and you want to do this transformation on your measurement into the global space in this instance from the vehicles. And from there, I want to know which landmark to reference it with.
Because we have our map. Our map has all these landmarks with IDs. I don't have the IDs. My sensors don't get the IDs. They just get positions of landmarks.
Yeah.
And I have to come up with some consistent view of the world where I can now label those landmarks the same way with my map, and now I have some truth to compare things to.
Yeah. So this would be a great time to kind of show this classroom concept. Over here. And so this kind of is a nice example of it, where we have this car and we also have this single particle. Now we're going to be doing this for many particles, but we have these landmarks here close by. 1, 2, 3, 4, and 5. And it's only sensing the ones that are closest to it. Basically, here's the observations it gets, and this is relative to this car's vehicle coordinate system down here. So
we're just paying attention to the car and not the particle for now.
Right. Okay. And basically, so if we have this landmark right here, we can go 2 on the X and then 2 on the Y, and we reach this landmark right here. And the same thing over here, if we go 3 and then down 2, we get this landmark, and we go 0 on the X and down 4. We transform these into the global coordinate system. So for example, if you're doing that for just this observation 1, this is our particle here. And we don't even have to use too much trig right here because they're just like at right angles. But we go down 2, and so we end up with 3 on the Y. And then we'd go over 2 on the right, and we'd end up with 6. So our landmark, our measurement right here would be somewhere around here.
So you're saying that, so 2, corresponds with?
The vehicle's coordinate system measurement for this landmark right here. And that would end up being transformed over here relative to this particle. And it's closest to landmark 1. So when we're doing our calculation of what that weight should be, it'll be associated with this landmark L1 right here. And we'll kind of go into some of the equations for that a little bit later. Right now, let's go ahead and dig into some code. So for the newest project, main.cpp is our main engine that we'll be using. And actually, you don't even need to touch this file. You can just leave it as is. And the only thing we'll really be modifying right here is the particle filter.cpp. But it's really nice to understand how main.cpp is working as well. So if you're familiar with the kind of the WebSocket interface, it's the exact same that we're using for the extended unscented common filter. So sigma position and sigma landmark. So the simulator ask you where X, Y, and theta are, it's going to have some noise, and it's going to be the same kind of sigma values that we're seeing here. Likewise, for the sigma landmarks, if we add and
so this in this line, this is basically when you submit for evaluation, this is the evaluator instantiating one of your particle filters, and then an instance of your particle filter class that you define in particle filter.cpp.
Yeah, that's right. And it's going to be what's localizing this vehicle. With h-on messages is something that WebSocket is using, and we're just passing these values that we created so we can use them in this continuous loop. So this will be happening every time step. So just a pointer to those objects that we created so we can modify them over time and they don't get overridden each time step. Here is where the meat happens. So this is where actually all the code is at. And when you first start this up, a PF is initialized or it's not. So it's not going to be initialized. And so we're actually going to be asking the simulator what the X, Y, theta values are. It'll be returning noisy values. And we need this, the first thing we're going to set up in our particle filter is pf.init. And we're passing in these noisy measurements to actually initialize our particle filter.
Those are analogous to what you'd get from GPS.
Yeah.
They give you some rough idea of where you are, but the goal is to get much better localization.
Yeah, that's right. So after we've initialized it, the next thing we do is look at predictions. So this is the other thing that we can ask the simulator. And this is actually noiseless. It's the previous velocity and previous yaw rate that the car was having. And then we can just pass it to his prediction step here. Now, one thing that I found very interesting, and it's kind of like an epiphany moment for me when I was looking at particle filters, is that this prediction is actually, you notice, it's passing in this kind of sigma position. And at first, this kind of confused me because I was thinking, well, this controls is noiseless. But we're actually adding in some Gaussian noise to that transformed position. And the reason that we're doing that, so the one thing I was kind of confused about with particle filters is when later we're doing the resampling of the weights and only the strongest weights survive. So at the end of that, wouldn't you just have one particle fill up your entire list if like the predictions was noiseless? But here we're actually using some jitter. And so from here, we can actually sort of generate new particles. So we don't have that problem where our list is just occupied by a single particle, because that would not be very efficient at all. So, and it actually works out very well, and it's very necessary here to add this. In fact, if you don't have that, I noticed that you weren't able to pass the project. So yeah, I found that pretty interesting. So after you do your prediction, this is when you're actually going to be checking out the sensed observations. So this is coming from the simulator, and there's going to be some noise associated with those measurements as well. These are the landmarks that's seen close to it. And we need to basically take these noisy observations and pass it into this update weights function. And so that's kind of the meat of this project, and that's what we're just kind of talking about earlier. And we'll go into some more depth of how to do that as well. And then resample. This part actually turns out to be pretty easy on C++.
Yeah, there's a great, so we should just say,
Mm-hmm.
what's the name of that?
Well, I can get it up on here.
Yeah.
It's in this resample. It's just kind of like this discrete distribution.
Oh, yeah. So basically just, it samples according to this. You have like an array of weights, right? And then it samples according to weights. So a weight that's of 2 is twice as likely to get sampled than something that has a weight of 1. Is that correct, what I just said? Yeah.
Yeah.
Okay.
So just based on the weight itself, that's its probability of getting chosen. Yep. So it's awesome that's just prepackaged in here. You don't even have to write your one.
It doesn't even have to be the probability. Like those weights don't have to be the probabilities. They just
it's just some of them
and figures it all out for you. It's really nice.
Yeah. So it's a great tool to be able to use on here. And so there's resample, and then basically we just check out all the particles that we generated, and we're looking at their weights. We pick the one with the highest weight, and that's our best representative for where the vehicle's actually at. And we just feed back the best particles x, y, and theta values to the simulator, and it graphs that for us. And there's some extra steps here where if you want to look at the association and the sense x and y, so these are like the landmarks that the particle sees, you could also add that in as well. If you don't modify the code, actually just won't do anything. So, but that's just like an extra debug, and it's really helpful to see that your transformations are correct. So cool. That's everything for what main.cpp is using. So let's kind of dig into particle filter.cpp, which we'll be modifying here.
This is the file that the student, you are expected to complete, basically.
Yeah, so we'll kind of go over some of the more basic stuff, and then when we're talking about update weights, maybe put a little bit more focus on maybe the classroom concept, and try not to just like indulge into the code unless there's any specific questions on how to do something maybe with the code. But here's the initializer. This is kind of where you're choosing. You pick the number of particles that you want to have. I found that like 100 was actually a pretty nice value. At first I thought 1,000, but
yeah. I just used 1,000. I didn't know. I'm impressed that it works well.
Yeah, and so the thing that you're thinking about here is the speed and efficiency. So if you have less particles, it's going to run quicker. If you have too few particles, though, and you're not going to have one that's going to represent it as well. So it's a balancing act right there. We're looking at the sigma position values, and we're moving the x, y, theta values relative to that. So that's kind of how we're initializing the particle to these random x, y, and theta that correspond to our uncertainty. And we know what our uncertainty is. This is given to you. And that's the same values that we saw in main.cpp at the top there. And so we don't have to worry about that too much. And so we go through each of those particles and we generate a new random x, y, theta that move along the sigma. And the weights will just start off as 1. And now we have our particles and weights, and it's initialized. So let's talk a little bit about prediction now. What do you do after it's been initialized? Here, like I was talking about before, we have this standard sigma positions that we're going to use to add a little bit of jitter to these particles. We also have the previous velocity and yaw rate. So in the classroom, kind of close to the end there, there's these equations shared and how to actually do the update. And it depends whether your yaw rate is 0 or not. Because if it's 0, you don't want to do any, if it's 0, it's pretty straightforward just to do the trig and see what the update is. While if it's not 0, you have a little bit more complex curvature forming, and you actually end up having this division by yaw rate. So if your yaw rate was 0, you definitely wouldn't want to plug it into this anyway.
Interrupt you guys real quick?
Yes.
So there's connectivity issues, which is causing sound to drop out. So I was going to relocate us to another room and let everyone know we'll have a brief introduction. That's okay.
Yeah.
Maybe if you can.
Sure.
Okay. From the hangout.
Okay. Hey guys, we're back.
Sorry about that. We're having some connectivity issues, but now we have a nice green background, so that's kind of cool.
Yeah.
All right.
So
Where were we? We're talking about the code, and Rahul has a question about why adding Gaussian noise improves efficiency. And can we go back to the code? There's a few places where you add noise. Scroll maybe back in the init step. So in initialization, the reason why you would add noise, you don't know where you are, right? The whole thing with particle filters is we don't know where we are, but we have a guess, and we also maintain it. We have some confidence in that guess. Now, the confidence in that guess is kind of represented by how tightly your particles are clustered. It's weird. It's not quite like a common filter where you can just say the variance is this number, but that's okay. So to represent that uncertainty, when we get our first GPS measurement, for example, we spawn these particles, and we spawn them with some randomness. We spawn them around our best guess, because that is where we think we're most likely to be. But we acknowledge the fact that there's a chance, we could be off, and so we want some particles that are like kind of doing other stuff, so that there's a good chance that they will have, that they'll be closer to whatever our actual position might be. We also, in the prediction step, we add noise as well. And the reason we do that, is like Aaron was saying, if you don't, let's think about what would happen if you didn't add noise in the prediction step. Okay, so initially, let's say we have a bunch of particles everywhere, and we get our sensor fusion data, and we have all these landmarks. And we imagine looking at the world through all of our particles' eyes, and updating their weights according to which of those particles are seeing the world as closely as we are actually seeing it. And we kill off all the ones that are, really far off. And then we make copies of the ones that are looking good with high weights. Now we make copies, and then if we didn't add noise, when we then, advance those copies further ahead in time, there'd be no purpose of adding the copies, right? They would just all be doing the exact same thing. And if you keep repeating this process of resampling, propagate forward, whatever, you're actually going to get more and more copies of the same thing, till eventually you just have one particle, n equals 1,000, or whatever your number of particles is set to. You're going to have 1,000 of the same particle, all doing the exact same thing, and it's not going to be doing exactly the right same thing. And that's the problem. It's going to be moving in a straight line with whatever velocity it had back when you thought it was looking good, and you're kind of stuck there. There's no hope of localizing then. You've collapsed to the wrong wrong location, really.
Yeah.
So adding noise, yeah.
That jitter really helps. It'll spawn new particles that are close to where you're moving, where you're transitioning, and so yeah.
Does that answer your question, Rahul? Oh, yeah. Sis got it. Okay.
Awesome. Cool. So I think that does it for just this prediction here. It's just noiseless control, but then we also add this jitter for the reasons that we were just talking about before. There's a couple other equations, like there's this update weights, and we just talked about resample. So really, those are the big things we want to look forward to. For update weights, instead of just kind of going over the code itself, I sort of wanted to maybe talk about, in a general sense, what was going on. And so that's kind of like this example here in this classroom concept where we have this single particle, and we're trying to figure out what weight to assign it. And if you go through this, so we just talked about how to transform this observation here into the global spectrum. So then it's associated with L1. But what do you do after that? Well, basically what we have is this multidimensional Gaussian that we're drawing from. And it looks like this. And it's based on the X and Y values you have.
Do that. Oops, sorry.
Yeah, and if you look at this, we have this mu X and this mu Y. This mu X and this mu Y, that comes from the association from the landmark that we have. It's a real landmark that we want to compare this with. And so if you notice, this is difference between our measured X, measured Y, and that associated landmarks X and Y. And it turns out that if it's like 0, you end up being at the peak of this three-dimensional Gaussian. So you're right at the top of this mountain, and that's where you're going to have your highest weight. So if they're right on top of each other. This is just a normalizer right here, and it turns out to make it so the volume of this three-dimensional Gaussian is just 1. And then everything else is just a spreading factor. So we want this X and mu X and Y and mu Y to be, the difference to be 0. We want them to be as close as possible. And if they're not, then we're going to fall off this three-dimensional Gaussian way over here, and our weight's going to be tiny.
So one thing to point out is that so you use this equation after you've mapped your, done the data associate, you've mapped what you're seeing to the map landmarks. Mm-hmm. And you do this for each landmark that you can see. Mm-hmm. And you maintain, so you kind of maintain this, you let these probabilities multiply each other. So, so it's your reward for getting all the landmarks right and for getting them all as right as you possibly can.
Yeah, so we're looking at this calculation for like this single observation, but we have more than one observation. In this case, we have 3. But in total, we have 5 landmarks, but we're only doing the ones that are closest in the car's vicinity. So to calculate the final weight, we take each of these observation calculated weights and just multiply them together. Mm-hmm. So if they're all really tiny, then a tiny number is being multiplied by a tiny number, it gets even smaller. And that's our final representation of what the particle's weight should be. So essentially, we're just taking this idea and we do the exact same thing in code. So what are some things to talk about? Well, how do you actually do the transformation from this car's like vehicle coordinate system, in this case our reference particle, to the map's coordinates? And it turns out it's just essentially shifting it based on the particles X and Y, and then also doing a rotation. So the first thing you could do is do a rotation around the origin of the particle's theta value. And then once you do that, you could shift it based on the particles X and Y. And then you can actually get like the global position for where it should be. And that's a gist of it.
That's the gist of it. Should we? I'm trying to think. Should we show at least that code that does the coordinate transformation?
Okay. And update weights.
Yeah, because I mean that's one of those things that this one.
Yeah. So like what we're talking about here, this is actually if you're trying to do your transformed observation X and Y. So like I was saying, the first thing you're kind of doing is this rotation based on the particles P's theta. Yeah.
So there's 2 components. This one, which is just the offset of the particle in the global frame. And then, sorry, I'll let you keep going on what you're saying here.
Okay. So yeah, you do your rotation based on the particle's theta. And so that's just rotating it. So like it's in reference to the global positions coordinates where X is going to the right, Y is going up. And then all we have to do is this horizontal and vertical shift. And that's easy enough to do just by adding on the particles X and Y values that we're seeing here at the end.
And if your code is almost working and you see just, it's totally not, so this is a problem I had, was with these minus signs and these plus signs and these signs and these cosines. It's easy to screw up the math if you're like sitting down on a piece of paper and maybe you drew the axis wrong or you just like, it's wrong. So yeah, that's the thing that you'd probably want to.
Yeah, and there's this great tool in the simulator where we can actually spot that. Let's say I messed that up, get it backwards.
That's what I did. That's very plausible.
Yeah. So let's go ahead and run make. And now we're going to run our particle filter, but we're doing the transformation backwards. We get this sort of spider looking thing, and let's kind of like pause this and just for a moment like look at what's going on. This is pretty cool. So these blue lasers here are mirroring these green, so we can see it's totally backwards. Yeah. There's this total.
Wait, what if you keep playing it? I'm curious.
It's gonna spider off.
Yeah, it's doing like all the opposite things than
Yeah.
what you want it to do. Yeah.
And these red show what it's associated with. So it's kind of like asking, what's the closest landmark to this point here? Well, it turns out to be this guy right here. And it's like, it's not right. Well, yeah. I guess if it's like this one, that turns out to be right. But like down here, it's like totally off. Yep. So watch it spider off here. And then so that's a nice debug tool to use in the simulator just to see if you're doing your transformations correct or not.
I guess, yeah, does anyone have any other questions? We don't want to walk through the code in too much detail because that's part of the point of the project. But if anyone has any specific questions about either concept or implementation, we can offer help where we can.
Change it back to camera mode here.
Yeah, sure. In the meantime, I think particle filters are pretty cool.
They definitely are, yeah.
I like that you can. It's interesting that you common filters, you need to at least feed it the the controls you're giving. Doesn't even need to do that with this. Just spawn a bunch of things, give it all the controls, and see what happens. It's pretty impressive that actually works.
Now, if you're doing this in a real life scenario, what kind of landmarks would you think about using?
I don't know. I've never done this in a real life scenario, but ideally things that
Sebastian kind of talked about lane lines.
Oh yeah,
remember? Yeah. And he was having some problems because he was generating maps of these lane lines that he was using as landmarks, and then all of a sudden they paved the road or something.
Yeah.
The map would be out of date.
Yeah. So you want landmarks that I guess are likely to be there tomorrow.
Yes,
that's a good idea. We've got other questions. Okay. Why is discrete distribution useful for resampling? Because it just does exactly what you want to do in resampling. In resampling, you have a list of particles or an array of particles that you want to make copies of. So I want to take my 1,000 particles and I want to kill some of them and make copies of others. And I want to make copies in proportion to how much I believe in each one. So that's how big their weight is. And this function just does exactly that. If you feed an array of numbers and say, discrete distribution go on this array, it'll give you an index into that array, and it'll do that proportional to the size of, or with probability equal to whatever number is at that position divided by the sum of the entire array.
Right. So if you had a list of say 1, 1, 2, 4, so what's the probability of pulling that first element, that 1? Well, it's just going to be sum of those list elements, which is 8. So it's going to be 1 divided by 8. So you have 1/8 chance of pulling that first element. But what probability do you have of pulling that last element, which is 4? Well, now it's 4/8. So you have a much higher percent, 50% chance of pulling that last element. And that's what that discrete probability function will do for you.
Okay. Lucas wants to know why not use the Gaussian probability to associate the observations to the landmarks instead of the Euclidean distance. And I think the answer is because Euclidean distance works.
Yeah.
It was working. I don't know. I did it that way because it worked. You're probably onto something, and your way might be better for real life data. I don't actually know. And if you have something, if you want to go down that route, it might work. But for the, this is a pretty nice, clean data. The map is reliable. The landmarks are literally just a coordinate, X, Y pair and an ID. So for this, Euclidean distance is fine, but yeah, I'm not the only way.
Pretty interesting, yeah, to try that a different way. And cool.
Rana asks, what about using buildings as landmarks? Yeah, buildings seem like they'd probably be a pretty good idea. Yeah, they don't really move much either, do they?
Yeah. And I think when the Voyage guys were driving the Udacity Self-Driving Car down El Camino, they had a pretty detailed map that they were using. So localization is pretty key right there.
Yeah. see what else. Any other questions? They could get demolished. So I mean, yeah, this is something we haven't really talked about. I guess there's a whole other field in maintaining your maps, right? You gotta update these maps as the world changes.
Yeah.
And you have to not let the absence of, if you don't see a building that you expect to be there, you have to make sure that doesn't throw off your localization entirely.
And getting really good map data as well. I mean, there's teams of people working on getting really accurate maps that even have the curvature down for the road and even like potholes and things like that. It's crazy. So there's teams that really strongly believe that without accurate maps of the environment that the self-driving cars won't be able to do as well, even though you have other people that say, well, it could just be done all through like vision and deep learning in that aspect.
Yeah.
So.
All right, looks like there's not any other questions coming in. So I guess we should, sorry about all the, it sounds like there were still connectivity issues that I wasn't even aware of. Sorry about that, guys. I know that's frustrating to happen. But I guess we can call it a day now, huh?
Yeah.
All right.
All right. Well, thanks everyone for joining today.
Have a good one.
Yeah.